Okay, well, I would like to thank the organizers of the conference, particularly Gil Strang and Cleve Moeller for inviting me to give this talk. Direct Methods for Sparse Linear Systems. Now it's also the title of a book I've got coming out by SIAM. Subtitled, and I didn't subtitle the book this way, the MATLAB Sparse Backslash. Informally, the book is being called the Sparse Backslash book. And I'm Tim Davis, University of Florida. So, what, after all, is a sparse matrix? Well, I like Wilkinson's definition. It's both short and sweet, practical, and also deeply theoretical. A sparse matrix is a matrix that allows special techniques to take advantage of the large number of zero elements. It sounds rather pedantic. But one class of matrices that this includes, which I'm not going to talk about, is what I would call structured matrices. A band matrix, okay, a triagonal matrix. Yes, it fits this property, but it's not, it's a very structured matrix I'm not going to talk about. Another interesting class of matrices that this excludes when you're looking at direct methods is random matrices. Imagine a matrix where the entries just appear randomly in a shotgun pattern in the matrix. Those types of matrices result in catastrophic fill-in, the introduction of new non-zeros and the factors that aren't present in the original matrix. And they take order n cubed time to factorize, maybe with a small constant. But they're not sparse in the sense that you can't take advantage of them. So I exclude those as well from this definition. This definition excludes those matrices, which is one thing that's interesting about that definition. Sparse matrices arise in a vast domain of applications. I'm going to talk about each one of these. I'll give you a coffee break at the comma. So by the end of the week, we'll hit the dots here. So, you know, obviously you can't even read this whole list. This list is a bit of a synopsis for the about 13 or 1400 sparse matrices I have on my website in the UF Sparse Matrix collection that people like me use to develop their sparse matrix algorithms with. I particularly like the human body parts there, got those. So a lot of interesting topics result or lead to the need to solve a sparse linear system. So the outline of my talk, what I'm going to do is I want to give to you the gist of sparse matrix algorithms. And the interesting thing about them, what I find fascinating, is that they're this blend, this mixture of numerical methods and graph theory, combinatorics. My goal of the talk is to explain to you sparse matrix methods from the ground up so that you can understand from the basic methods all the way to what goes inside backslash. One of the common threads that's you're going to see over and over again is the lower triangular solve, to solve Lx equals B, or Lx equals L backslash B in MATLAB notation, where L, X, and B are all sparse. Now, what's interesting about this problem is that in order to compute X, you must know it first. Well, more precisely, you need to know the non-zero pattern of X first in order to compute it efficiently. If you don't know the non-zero pattern of your solution, you can't compute the numerical values efficiently. If you do know the non-zero pattern of X, then the work is order flop count, which seems like an obvious goal. But this is not obvious, because inside these methods are not just the numerics, not just the floating point operations, but the graph theory and the combinatorics as well, and all the data structures. I'll next look at sparse LU factorization, which will rely upon, or at least this one method of sparse LU, and there are many methods. This method will rely upon this lower triangular solve. It's called a left-looking algorithm. We'll use partial pivoting. Now, it needs to be preceded by fill-reducing column ordering. And I'm not going to talk about that because that's a topic in itself. If the triangular solve is done efficiently, the time to do this algorithm is order n plus flops. And that n, in this case, is not a problem, where it was in just the lower triangular solve. If this lower triangular solve took, for example, order n plus flop count, it's used n times here in the LU factorization. So you'd end up with an n squared time LU factorization. If you gave me a tridiagonal matrix and I told you, oh, I'm going to take n squared time to factor it, you wouldn't use these methods. Then I'm going to look at Sparse Cholesky factorization. Quite a gamut of different methods, both an up-looking and a left-looking algorithm. Again, this has to be preceded by fill-reducing ordering. This, by the way, is an NP hard problem. Inside backslash is the heuristics for solving an NP hard problem. Which is to reduce the introduction of new non-zeros in the factors which aren't present in the original matrix. It, too, relies on the lower triangular solve. And it takes order flop time if you do it right. Now, these previous three methods here aren't extremely efficient on high-performance machines because they don't use dense matrix kernels. Those kinds of methods, dense matrix operators, matrix multiply, so, for example. Methods that do those are, for example, supernodal and multifrontal methods, which both are used inside backslash. These use what are called the BLAS, basic linear algebra subprograms. These are things like dense matrix times dense matrix. And they're used, in the sparse case, on submatrices that arise or that appear inside the sparse matrix. I'll look at both, give you the gist of supernodal and multifrontal methods. So up next, sparse matrix data structures. How do we store these beasts? There are many different ways of storing a sparse matrix. This is the one I'm going to describe to you is the compressed sparse column form. And in that, every column is stored as a compressed sparse vector. So imagine a collection of columns. Each column is a list of two things. You've got both the numerical values in that column of the non-zeros, and you've got the row indices in which they appear. And then just compact that down. It's just a list of non-zeros and the row indices. And that gives you one column, a sparse column vector. And then glue those together, you've got yourself a sparse compressed column matrix. And in terms of a data structure, AI is an array of all the row indices, and AP tells you where within that array the column starts. And then this range of entries gives you the row indices of the jth column. And in the same positions, you have the numerical values of those entries. So here's an example. First, though, as a consequence of this data structure, which is the data structure used to store a MATLAB sparse matrix, getting the jth column of matrix in MATLAB is very simple. You just look it up. Imagine now what you would have to do to get the ith row of the matrix. There's no cross links across each row. You have to go down every column. Oh, is row I in this column? No. Is row I in this column? No. It's very slow. The best speed above 100 I ever got on someone's MATLAB application, they were computing Google page ranks and accessing row I of the matrix over and over again. I said, don't do that. Transpose the matrix and get the ith column instead. It was much, much faster. So here's an example. It's not sparse in the sense of Wilkinson because it's too small, but it fits on the slide. Here's the data structure according to this format here. You can see here pieces of the matrix. So here's the first column. It's positions 0 through 2 of these two arrays. Rows 0, 1, and 3, it's zero-based. And there are the numerical values. There's the second column, column 1, if you will, in zero-based notation. There's column 2, and there's column 3. And 10 is the number of non-zeros total in the matrix. So with this data structure now, I'm going to show you some different algorithms that, of course, are very careful not to try to access the ith row of a matrix, except in very special ways. The one is a sparse lower triangular solve, x equals L backslash B. Here's a MATLAB script that does this, almost completely MATLAB, except it's got this funny not equal sign. It's not real MATLAB syntax, but it just looks nicer. So imagine B is sparse, and x, in fact, is a sparse vector, but it's stored in a workspace of size n. And we keep track of where in x the non-zero values are. So the list somewhere of those values. So you have to iterate across all the columns of j. If xj is non-zero, you've got to take x sub j, multiply it by the jth column of L, subtract it off of x, and you're done. That's the lower triangular solve. So how much time does this algorithm take? Well, this first iteration here, or first assignment, x equals b, takes time proportional to the number of non-zeros in B. That's small. This innermost loop here, this work here done on the sparse scatter operation, does take time proportional to the number of flops that are performed. Multiply scalar times this sparse compressed vector and scatter those values and subtract them into this large work vector x, and you've done this step. So what's left? The j loop and the test if xj is non-zero. So the total work of this is order n plus flops, which is not acceptable. And so there's the problem, for loop and the test. If only I knew where x was going to be non-zero, I could just iterate across those j's for which xj is non-zero, and I would have an optimal algorithm. So how do you know a non-zero pattern is a solution before you compute it? Well, the answer is to look at the combinatorics before you do the numerics. And ask yourself the question, where does x become non-zero? X becomes non-zero in 2 places. It becomes non-zero here in this statement. If b sub I is non-zero, then x sub I is non-zero, right there. It also becomes non-zero here in this statement. If xj is non-zero, and there's an Lij that's non-zero, then you get a non-zero value that you subtract off of x, so xi is going to become non-zero. Now, there's a subtle lie to these 2 statements, and the lie is that 3 minus 3 is non-zero. If you compute it, in other words, that's what I mean by x sub I not equal to 0. It's been computed, numerical cancellation is ignored. So non-zero plus non-zero is always non-zero. With that assumption, which is a very simple assumption to make, these 2 logical rules hold. And the pattern, where things are non-zero, does not depend on the numerical values, but where they are only. So all we have to do, just gives you a chain of logical implications, starting with B. Follow those chain of logical implications, you found where x is non-zero. And the way to follow that chain is to cast this as a graph traversal problem. So think of a graph, G, that has an edge from j to I if Lij is non-zero, which is really the graph of L transpose, but that's the graph I'm interested in. So this is, and now consider the case, now consider some notation. B is the set of non-zeros of B. This calligraphic x is the set of non-zero rows of x. And then with that notation, this is the answer. X is the reach in the graph of the nodes of B. Let me explain. This first rule says, put your fingers on the nodes of the graph corresponding to non-zeros in B. I'm watching you. You're not doing it. No. Put your fingers on the nodes of the graph corresponding to non-zeros in B, and then traverse paths in the graph, asking yourself, where can I get to from here? All the nodes you can reach via paths in the graph, starting at the non-zeros in B, are non-zero in X. And the traversal of this graph can be done time proportional to the number of edges traversed, which is not the whole graph, necessarily. And it can be accomplished with a depth-first search, in particular, which has other nice properties I'll show in a minute. So here's an example to kind of illustrate this problem. Suppose B sub 4 is non-zero. That's this green entry right here. If B sub 4 is non-zero, where can you get to from here? You can get to these red nodes. So this says that X has the non-zero pattern 4, 9, 12, 13, 14, which is certainly not the whole graph. This graph could have 1,000,000 nodes, and you could perhaps find 5 nodes to visit, and you're done. You spend far less time than order n to compute that. Suppose also that B sub 6 is non-zero, the other green node. Then you can also reach nodes 10 and 11 from node 6. To notice, by the way, the connection between this matrix and the graph, you see here, for example, from 1, 3. L3, 1 is non-zero, so there's an edge from 1 to 3. There's an edge from 4 to 9, so that means that L sub 9, 4 is non-zero. So this is just a graph of this matrix. And in fact, the data structure represents both simultaneously. So then, why did I not list this x in a sorted manner? The algorithm says I go from j equals 1 to n. Can't I sort the thing? Don't I know how to sort? Yeah, I know how to sort. Takes too much time to sort. The only thing that's critical here is that x sub j has to be computed before you use it. That's all you need to know. You don't have to do this j in this order. All you have to do is follow what's called a topological order. But that's what a depth first search will give you. If you look at this list of non-zeros at 6, 10, 11, 4, 9, 12, and so on, you'll see that all of these edges in the graph that go between these nodes go from left to right. 6 to 10, you've got an edge from 10 to 11. There's no edge from 6 to 4. So it can appear in that order. This is a topological ordering of the nodes that are in green and red in that figure. So here's the original problem. The time is unacceptable. We need the non-zero pattern first. So we compute it first using the reach. And then we iterate instead of all j, we go from j in the non-zero pattern of x. How do you compute the reach? Well, it's just a depth first search. So you start with all the non-zeros in B. If the node is unmarked, you do a depth first search at node I. To do a depth first search at node I, you mark the node and you look at all the outgoing adjacencies. If it's unmarked, you do another depth first search, push j onto the stack. You've got x in topological order. Total time now is order flop count. Why? Every time you visit an edge here in the depth first traversal, you're accounting for one rule, one of those logical implications. It says if xj is non-zero and there's an Lij, then xi will be non-zero. That's exactly 2 floating point operations. So every edge you traverse in the depth first search corresponds to exactly 2 floating point operations, in the numerical computation. So the time for the depth first search is proportional to the floating point operation count, not n. Imagine if this matrix were a million by a million, but only b sub n was non-zero, the last entry. You do constant amount of work to get the solution. You do one flop at most. Well, L is, in this case, is assumed to be unit diagonal, so there's actually no flops at all. But neglecting that little caveat, you do no work, or constant amount of work, constant floating point work, and you have the solution much less than order n time. So this lower triangular solvent forms a part of what's called a left-looking LU factorization. This is by Gilbert and Pyrels. It forms a part of backslash, but not a fundamental core. I'm explaining a simpler method than actually what's in backslash. But this is also still in MATLAB. And it's also a very useful algorithm, particularly for circuit simulation matrices. This is actually better than backslash. It's a left-looking algorithm in the sense that at the kth step, you compute the kth column of L and U using or accessing columns 1 through k minus 1 to the left. Here's a MATLAB description of the algorithm. It's actually a functional description. It's even got the 3 little dots. It doesn't have any pivoting. But you can see at each step, the kth step, you do a triangular solve with the partially constructed L, using as a right-hand side the kth column of A. Once this x is computed, the first k rows of it become the kth column of U, and the rest of it become the kth pivot column of L, which is then divided by the pivot. It's left-looking because this is the picture. Red means we computed. Gray means it's being accessed, although actually the figure I should have just graded the L part because U is not accessed anymore. This doesn't do partial pivoting, but it could. And I haven't shown the column preordering to begin with, Q, but it could be done. To compute P, all you need to do is swap on X to do the partial pivoting. So putting these tools together, you can also do a sparse Cholesky factorization. Let me show you how that's done. So here it is a sparse Cholesky factorization. A is going to be factored into the product of two lower triangular matrix times itself transposed. A equals L transpose. And to derive this algorithm, chop up each of these matrices into a 2 by 2 block, where these leading blocks here are of size n minus 1 by n minus 1. So L22 is a scalar, A22 is a scalar. L12 transpose is the nth row of L. Then do the matrix multiply, and you get 3 equations. One of them is coming from this first part. If you multiply, you get L11 times L11 transpose equals A11. So recursively, factor that matrix. Get that factorization. Then extend that result by this formula here. If you take the matrix product of this first row and the second column, you get L11 times L2 equals A12. So what do we have here? We know L11 now. We don't know L12, and we know A12. This is a lower triangular solve for the nth row of L. So solve it. And then when you're done, the L22 entry is just a sparse dot product of the nth row. Subtract it off from the nth diagonal entry, take the square root, and you're done. That's a sparse Cholesky. So converting this recursive algorithm into an iterative algorithm is pretty simple. You just then go through k equals 1 to n. You solve for the kth row of L. And then you do the sparse dot product. You could call this a presidential algorithm, right? Because it's operating on the rows of L. So that's the it'd be better, I suppose, if it was working on the rows of L transpose than it'd be the rows of L. So it's an uplooking method in the sense that at the kth step, you're computing the kth row, and you're accessing rows 1 through k minus 1 above you. So we know how to do this efficiently, right? I just showed you how to do the sparse triangular solve. It turns out that a sparse dot product is very simple to do, so we're done, right? This is all order flops. Yes, we could be done. Order flops, that's our goal. But we could do better. This triangular solve can be done yet more efficiently. Not the numerics, but finding the non-zero pattern can be done more efficiently. And this is one thing, there's many things, that motivate what's called the elimination tree of a matrix. This elimination tree comes up in a vast range of sparse matrix algorithms. Here's one motivation for the tree. The goal is you want to compute the non-zero pattern of this x equals L backslash b, where b is sparse, L is sparse, x is sparse. Well, if L comes from a Cholesky factorization, which it does, that L11 matrix, partially constructed factor, then it turns out you can compute the non-zero pattern in time proportional to the size of that pattern. That is the number of non-zeros in x, where the bar here on x means that not the size of the set, or the number of non-zeros in the vector x. So let me show you where this tree comes from. It comes from a pruning of the graph of L. Consider computing the kth row of L. This is the picture I had before. You've got the solution is going to become the kth row of L to this triangular system. And this triangular system you're solving is rows 1 through k minus 1 of L. So if x sub I is non-zero, that means LKI will be non-zero, because that's exactly, in fact, the same entry. It's going to become, it's copied. You're solving for L12 in this step. So you're solving for the kth row of L. So if x of I becomes non-zero, that will be LKI. So if that's non-zero, if LKI is non-zero, x of I is non-zero. Simple rule. Now, use that other rule we had from the sparse triangular solve. If x of I is non-zero, and there's an L sub ji that's non-zero, then xj will be non-zero, following one edge in the graph. Well, xj non-zero, that's the same thing when it's flipped down to the result as LKJ, because that row, this solution x will become the kth row of L. So xkj being non-zero will mean that xj is non-zero. So now I have, the result is that these two entries, lji and lki, imply that lkj will be non-zero. And now think of the graph of this, or think of the subgraph of the nodes I, j, and k. And think about the reach of node I. Where can you get to from node I? There are three edges here of interest, one from I to j, one from I to k, and one from j to k. If I deleted the edge from I to k, I don't change the reach of I. I can still get to j of k just by a longer hop. The hop distance doesn't matter. The question is, can you get there from here? And you still can. So let's delete the edge lki, which will speed up our graph traversals. But now there's nothing special about lki except that k is bigger than j. So in fact, all of the entries in column I below the first entry, lji in this case, can be deleted from the graph. So you have a graph now, think of it, with one outgoing edge from every node. And the graph, the matrix is lower triangular. So edges always go from a lower number node to a higher number node. So what is it? It's a tree. That's the elimination tree. Now rather than searching a general graph with the depth first search and taking time proportional to the number of edges and so forth, all you have to do is search a tree, which is time proportional to the number of nodes you traverse, because there's so few edges, not the number of edges, which is then proportional to the number of entries in the resulting non-zero pattern, not the number of flops required to compute that solution. So this defines the parent of I is the smallest j bigger than I, such that lji is non-zero. That's the lji I showed you there. That's the parent. J is the parent of I in this case, assuming that that's the first off-diagonal non-zero in column I. So this means that the reach in the graph can be computed in time proportional to the number of nodes in that reach set, which is very nice. So this gives you a Sparse Cholesky factorization method. Here's an example of an elimination tree. This is the matrix A. It's a symmetric matrix, of course, because we're doing a Sparse Cholesky. It's for symmetric matrices. And here's the factors. And now what I've done in red is I've shown entries that appear in L that do not appear in A. Those are called fill-in, and a pre-ordering tries to minimize that. Minimizing the number of red entries in this graph here is that NP-hard problem. And there's the elimination tree with all the parents here shown in green in the matrix L, and 5, for instance, is the parent is a child of 8, and so on. So Sparse Cholesky factorization now consists of 2 steps. There's a symbolic analysis step. You've got to find the tree. I haven't shown you how to find the tree, except that it's just dependent on the matrix L. But you don't actually need L, and this is the interesting thing, to find the tree. I don't have time to go into this method, but the tree of A can be found in time proportional nearly to the number of edges in A, not in L. And nearly here, it does have a technical definition. Really, the time is the number of non-zeros in A times what's called the inverse Ackermann function. All these things that come out of algorithms and data structures and combinatorics are all stuck in here. The next thing is needed is a depth first post-ordering of the elimination tree. That takes linear time and the number of nodes. That's followed by computing the number of non-zeros in each column of L. That could be done naively in time proportional to the number of non-zeros in L, using those elimination tree traversals I just showed you. Every row takes time proportional to the number of non-zeros in that row. It can be done yet even faster than that if you don't want just a pattern, but how many there are in each column can be done faster. And that's, again, a fairly elaborate algorithm that I can't touch on. I haven't showed you at all how to do these steps of the fill ordering, the E-tree, or the column count, or for that matter, even the post-ordering. Some methods then go on to find the actual non-zero pattern itself, which is time proportional to the size of the pattern, or more precisely, its representation, which can be smaller. Then this is followed by the numeric factorization. I've already shown you an up-looking method. I'm going to want to show you next a left-looking or supernodal method, and this is the method the supernodal method is what's used in MATLAB. Actually, MATLAB uses both of these methods. It picks which one it feels is the right one to use. And I'll also show you the right-looking multifrontal method, which is a different method altogether. So here's a left-looking Cholesky. I'm just going to give you the gist of this method. The basic gist of the method is, again, you're computing, it's left-looking, so you're computing the kth column of L now, not the kth row, using this shaded region here of L to the left. So that's why it's called left-looking. This is a MATLAB, or pseudo-MATLAB. It's got a statement here for j in reach of L. That could easily be translated into a same one-line MATLAB expression if you wanted to. But the idea here is that you still need the non-zero pattern of the kth row, because what you need to do, this next step here, is not a triangular solve, it's a matrix vector multiply. You need to take this kth row of L, multiply it by this entire shaded matrix, where of course it's striped because if there's a zero here in the kth row of L, you don't need to multiply it by this kth column, because 0 times a column is nothing. And then that matrix gets subtracted off of X. Once that is done, you compute a scalar Cholesky factorization. It's called the square root of the diagonal here. And then you divide by the pivot. And you've computed the kth column of L, and then you go to the next k. Now, a supernodal method is based on the observation that often in practice, and this comes up, for example, in solving a 2D or 3D discretization matrix, it comes from that type of application, that many columns of L have the same non-zero pattern, particularly near the end of the factorization. And the post-ordering will place those next to each other, and what you end up, the post-ordering of the elimination tree, what you end up with then is a chain in the elimination tree of columns, each of which have the same non-zero pattern, excluding the upper triangular part. This gray block here can be stored as a dense submatrix and operated on as a unit rather than operating on each column at a time. That unit is a dense submatrix, and dense operations can be applied on it. So let me just give you a picture of how this method works. It's a block left-looking algorithm, so it looks just the same as the left-looking algorithm, except these regions here are not individual columns or an individual row, but a whole block. So I've got, say, W columns of L within a supernode, from, in this case, columns K1 to K2, minus 1, I guess, the way I've drawn it. The first step is not a matrix times vector operation, but also sparse, but a sparse block matrix multiply. So you've got a sparse block matrix here. Each block is a whole supernode, times a block matrix here. Instead of the kth row of L, it's a block matrix, where these dots now are matrices, not scalars. Take this matrix, multiply it by that row, add it to the red matrix. And then you've got the update. Then you've got to do a dense Cholesky factorization of the diagonal part. Of course, in the scalar case, that's a square root. But in the case where this is a matrix, you've got to do a little bitty dense Cholesky factorization. Although it doesn't have to be small. It can be a good part of the matrix that you do all that work in. And then dividing by the diagonal is not a division, it's a triangular solve to do this operation here, which can also exploit dense matrix kernels. It's a dense solve. So each of these three steps are exploiting dense matrix operations. Now, I probably should say, so what? What's the big deal about dense matrix operations? Well, they can be coded up very efficiently to exploit cache and memory hierarchy, which exists on all modern computers. It's also good for parallelism. These dense submatrix operations can operate at a performance that's very close to the theoretical peak of the machine. Backslash, for example, on an AMD Opteron, dual core, 10 gigaflop theoretical peak, can operate at about 6 gigaflops. That includes all the combinatoric work. So it's pushing the limits of the machine. Here's a very terse view of the multifrontal method on one slide. It's not a left-looking method. It's what you think of when you think of Gaussian elimination. You take the pivot row, you multiply it by each entry in the pivot column, and you subtract it off of the rest of the matrix. Well, that subtracting off of the rest of the matrix is not done with a large sparse matrix, but it's done in small, dense submatrices. So here, for example, is node 1 in the tree, turns into this 3 by 3 dense frontal matrix, where the entries 1, 6, and 7 are the non-zeros in column 1, row 6, row 7. One step of LU factorization can be done, or Cholesky factorization, in case you'd only store half of it. One step can be done within this dense frontal matrix. You've left with a little 2 by 2 block, which is the update, the Schur complement, that's to be added to the rest of the matrix. It's not added back to the global matrix, but it's held here until it's assembled or added into the frontal matrix of the parent. If you notice, all these white circles, 6 and 7, in rows of columns 6 and 7, all find their home, a place, right here in their parent. The same thing with node 4. Rows and columns 6 and 10, those 4 entries, all find a home in their parent. And that's because of this, of the way filling works. The parent is always a superset of children. Now, sparse LU, when you have an unsymmetric matrix, is a little bit different. This is UNFPAC, or a picture of UNFPAC. It's a very terse picture. This is about 50,000 lines of code to implement this method. This is used in backslash as well, when you have an unsymmetric matrix. And when you have an unsymmetric matrix, the fronts become rectangular, and things change. You don't have the case where data needs to be assembled just by the parent, but it may need to wait until an ancestor in the tree. This method also needs to handle pivoting. In this case, the non-zero patterns can change. If you're doing Cholesky factorization in multifrontal case, you don't have to worry about numerical pivoting, and things are a lot simpler. So let me summarize all this. Let me bring all this together. X equals A backslash B when A is sparse. This is what I want to literally talk about, is the backslash algorithm in MATLAB. So how does this thing work? How does A backslash B work? Well, it's a very fascinating meta-algorithm. If A is diagonal, you're only interested in doing a row scaling. So that's what's done. So they check to see, is the matrix diagonal? Okay, row scale. If it's banded, the matrix is converted from this sparse compressed column form into a dense band matrix, a structured sparse matrix. And LAPAC is called. If A is upper or lower triangular, then a lower triangular forward or back solve is used, upper or lower triangular. If A is rectangular, then a Givens-based QR factorization is used by Gilbert. If A is symmetric and it has all positive diagonal entries, it might be symmetric positive definite, but we're not sure. So let's try Chol inside. And that's either a supernodal method, as I described, or an uplooking method. And both of these methods are inside Cholmon, which is my Sparse Cholesky factorization package. The method picks automatically between these two, depending on the number of flops that are going to be performed and the number of non-zeros in L. And precisely the ratio of those two, which gives you kind of a measure of cache reuse. Flops per non-zero in L is a very accurate way of choosing between these two methods. If none of these fit, then we use LU factorization, which is either multifrontal method or the left-looking algorithm I described to you, depending on a user-selectable switch. Usually, by default, it uses UNFPAC. And most of these methods, so if you want to actually see how does backslash work in MATLAB, if you want to see all the codes, you can go download most of them off the web. I asked the MathWorks once, well, how many lines of code are there behind backslash? They couldn't tell me. Not because it's a secret. They can't count that. I mean, what do you count? Do you count all of LAPAC? What parts do you count? It's not a trivial thing to figure out how much work is there. So off the top of the, unless you go digging, it's not easy to answer that question. A lot of these things are going to be, are talked about in my upcoming book, Direct Methods for Sparse Linear Systems. It's coming out this fall from SIAM. One other topic I'd like to mention really briefly is the Sparse Cholesky update downdate. This is work I've done with Bill Hager at the math department at UF. So this is a little different problem. You're given already the Cholesky factorization. You've computed it somehow. And you want to compute the factorization of another matrix, which is a low-rank change from your first matrix. This problem comes up in optimization methods, sensitivity analysis. Wilkinson thought that methods like this, considered methods like this, among the most important methods in linear algebra. What's interesting about it is that time to modify the factor takes time proportional to the number of entries in the factor that change. It's rather like the triangular solve. In fact, the columns that do change are exactly this, come from the sparsity pattern of the triangular solve L backslash W. So the triangular solve is here too. That's one reason why I wanted to mention it. This triangular solve sort of threads through a lot of these different methods. So direct methods for sparse linear systems. X equals A backslash B. It's a, as I said, a fascinating blend of numerics plus graph theory. My goal, which I hope I've reached, is to show you sparse matrix methods from the ground up, the numerics and the graph theory. I show you this thread that walks all the way through it, the lower triangular solve. I showed you how that could be used for sparse LU factorization, the left-looking method. I showed you how the triangular solve could be used for sparse up-looking Cholesky factorization. And I also gave you the gist, not the complete description, of supernodal and multifrontal methods, both of which are used in backslash. And I gave you a little bit of a glint of the Sparse Cholesky update downdate, which in MATLAB is called Chol update, although this doesn't work on sparse matrices, just dense matrices. And I gave you a little pointer to my book if you're interested in any details. So are there any questions? Go ahead.